these developing countries often have to walk long distances to find available water. More often than not, this available water is contaminated and is unsafe to drink. We wanted to tackle this issue by designing a bicycle attachment that will purify and transfer water as the rider pedals. And we hope that by using our project, they can improve the quality of life until a more permanent solution can be established. The motivation behind our H2Go was simply the alarming statistics we found while doing some research. For example, 768 million people still to this day don't have safe drinking water. Also, every 21 seconds a child dies from a water-related illness. Now, the main motivation behind the transportation needs were the jerry can, which is the main water tank that they use for water collection, weighs over 40 pounds, one full. Now, for a global learning aspect, we hope that with our project we can bring awareness globally about this water crisis, and that we can create an affordable temporary solution for the purification and transportation of water, hopefully by using recycled materials if possible, and adding a manual in 3 different languages, English, Spanish, and French, because our potential areas of use would be the Sub-Saharan Africa, South America and the Caribbean, and parts of Asia. There are 2 current examples that we have looked at while doing the research. It's the Cycloclean and the Aqua. The Cycloclean is manufactured by the Japanese company Nippon Basic, and the retail price is $6,600, which is very, very high. Now, this bicycle only works stationary, and it has no way of transporting any of the water that's filtered. Now, the Aqua was made for the 2008 Innovator Die competition, which it's capable of storing water, as well as transporting it and filtering. However, the design makes it much too expensive to be mass-produced, which is why the idea was basically abandoned after the competition. Now, we wanted the first stage of our system to be a pre-filter. Now, the purpose for this is to eliminate any large particles from entering the filtration system, thus ensuring the longevity of our filter. We had 2 different design alternatives for this. The Filtration filter, which uses natural resources such as rocks to filter water, and the second one was the sediment filter, which uses stages to eliminate any from large to small particles. Now, the final design for our pre-filter, we decided to use the idea of the sediment filter. We put 2 stages. Now, the materials we used were PVC pipe and reducers, as well as different size meshes, in order to filter as much large to small particles as possible before any water enters our system. As you can see, the pre-filter is also shown in our project. Now, when we research filters, we wanted to keep 3 things in mind: the cost, the life rating, and the required pressure for its use we could meet with our system. Now, we looked into the McMaster car water filter, which it's a powerful filter, but it requires over 30 psi of pressure for it to work, and the cost is over $185. And also, we looked into carbon filters as well, because they are excellent for heavy metal filtration. However, we also saw that a carbon filter that will last long, along our desired life rating, was also way too high. So finally, we came across this Sawyer 3-way inline filter, which actually only costs $60. And it has minimal output pressure needed, which means that the 11 psi that our system gives us is actually ideal for its use. Now, this particular model also has a 0.1 micron absolute hollow fiber membrane, which removes 99.99% of bacteria and protozoa. It's lightweight, and on top of everything, the manufacturer guarantees a 1 million gallon lifetime.
Analyzing our car body as a whole, we had to make sure that we did analysis on every single piece: the body, the gearing, the axle, as well as the bearings. And we had to restore certain pieces to keep our green initiative, and we're going to go into that in the assembly process. Our first design alternative was the sidecar design. We chose this because there was 3 points of contact in the ground at the same time. The problem that occurred with this is a wider body, so that narrow paths, rougher terrain might not be ideal, as well as possible steering issues when you put water on the right side. Our next design was the one-wheel trailer design. This was a much more compact design, solving the water issue as stated earlier, but tipping over might have been a problem, as well as minimal weight load capacity, and finding a way to retrofit it to the pump was an issue. So that led us to our final trailer design you have here with a beefed up frame, as well as allowing us to put an axle in the center that allowed it to make a self-incumbent machine, as well as giving us rigidity and strength. So when we did our card body analysis, the first thing we had to take into consideration was our water jugs, exerting an external force downward on the platform, as well as the rolling resistance because of this weight, and we did some SolidWorks designs for that, shown here. Our Von Mises stretch, you can see the edges begin to fold out, and as we move to our displacement, that's where the real trouble comes in, where you can see, again, the trend continues. In the center, it's fairly rigid, and then we move to our equivalent strain. Again, it's just kind of the same scenario, so that meant that we needed to make sure we provided support upon the edges as well as in the center to keep everything strong and in place, as well as keep congruency and integrity of the cart. We thought about bending the pipe at first at 90-degree angles, but again, in congruency purposes, we wanted to make sure it stayed intact. This is our cart skeleton, and just to the SolidWorks test, we did some weight bearing tests, upwards of 900 newtons. Stood on it on blocks, such as shown there, held up just fine. So then, our original thought was to create a singular axle with an outer housing around it to attach to the cart, and our main issue was figuring out how to fit it to the cart. So we looked around, and we actually stumbled upon this old tricycle design here. As you see, it's pretty beat up, but we thought, what better way to go with our green initiative as well, by recycling old materials and making it work. Here's some of the parts that we have. Actually, the sprout gear is the one that's on this cart today. The bearings were shot completely. We had to replace those, and our reverse threads were messed up. So this is our housing afterwards, and the picture before is all rusted and nasty. And we worked with Professor Ziccarelli at the EMC to help us reverse thread our axle again. And our axle assembly, if you look at the picture in the top right, you can see that the right side wheel is the driver in this case, and the left is held on by the bearing. We have 4 points of contact, with the main two coming in the middle, while the other two on the outer edges are there to combat any obstacles that get in the way. Again, this was just all incumbent, too easy to pass up. It would allowed us to save a lot of time and money. So when analyzing our gear analysis, as you can see, that's a gift of our gear working together. Our main issue at the beginning of this project was figuring out how to retrofit this to the bike and stay on. And in this case, we actually were able to create a device that can be input to any moving object, any moving vehicle, even by hand if you have to do it. Gears are set up so that as the axle rotates, the pump shaft rotates along with it, powering the peristaltic pump due to forward motion. We had to take into consideration our moment of inertia, because different people with different weights and different strengths are going to be doing this, and we're using 5 gallons of water, which can get heavy at times. And also our angular velocity, because it is still a somewhat slim design, but the wheels are larger, so your frequency of revolutions will be fewer and far between. We also did a static load on the blocks of the axle shaft as a whole, and 900 newtons, and still held up well. Here's our bearings that we replaced with. Obviously, the static and dynamic load is way above anything we need, but it fit our 5/8 inch axle, as well as was relatively cheap and cost effective. And here's our final cart design. We chose to go with the wood platform because it was easy for us to work on, cut into, as well as it's tempered wood, so it'll stand up to any elements. We have a coating on it. And we have our pump mount on there, have that secured in place with the L brackets to keep it from going anywhere during rotation.
When researching a pump to power our filtration system, we had to take into account the mechanical aspect of this project, which was how we were going to retrofit to the bicycle, or in this case the cart, which ended up being our final design. So we chose a peristaltic pump for that reason. It's very easy to power mechanically. Also, it has a low maintenance cost, it's easy to clean, and it can pump about 60% of solid material. When looking into peristaltic pumps, we found that they were too expensive and really didn't meet our design criteria, so we chose to build our own. Design considerations when choosing our final design for the pump was the number of rollers, optimization of the size for the rotational speed of the cart, the occlusion setting, which means the squeezing of the tube, and not only the size of the tubing, but also the material of it. When doing research for the peristaltic pump, we found very few governing equations for it, very little information on it. These are two of the governing equations. This is the equation for flow rate and the equation for percent occlusion, which is how much it squeezes the tube. Because, and as you'll see later, we chose a spring-loaded roller, we negated the occlusion setting for our final design. These are our initial prototypes. We wanted to test out the equations. We really didn't have much information on it. So we built a very cheap prototype to test out flow rates. Initially, we used a vinyl tubing and found that it needed too much torque to turn the internal components, so our center block kept breaking. So we've moved on to a silicone tubing. We used this pumped well. We used 2 rollers and 4 rollers to test out flow rates. Unfortunately, throughout our testing, we found that the housings started failing, basically. So we couldn't get a whole lot of data points on this particular prototype. Also, we found that without priming the actual pump, we could not start pumping. So we needed to incorporate a siphoning device for our final pump. As I just spoke about the housing, we knew that it had to be very rigid, very strong, and that long-lasting. So we used 9-inch diameter PVC tubing. It's 1/2 inch thick, so it's very, very strong, with a base where all the components are bolted onto that is 1/2 inch thick PVC sheet. To this is bolted a 4-bolt flange bearing with a 5/8 diameter bore. The roller assembly is attached to a 5-inch diameter hub, and here's our roller assembly with our spring. Here is a slow motion video of the pump working. As you can see, we have really good occlusion throughout the entire process of the contact of the roller to the tube. And here is a picture of the internal components put together, which is the bearing, the hub, and in between we put shims basically, because we needed space for the roller mechanism. We put it there just in case of failure, because both the hub and the bearing are with set screws. And as you can see, the final assembly of the components, you can see it here. We have a very malleable piece of galvanized steel holding our pump together. And on the other side, you'll see the block held together with L brackets. It's there to counteract the pump basically wants to move as it's being powered by the gears. So that's to counteract it. It has a bearing in the center, so the shaft goes through it.
Okay, so in continuation of our peristaltic pump, as mentioned before, our first prototype kept failing, so we built the second one. We did 4-wheel design and then a 2-wheel design using 60-second intervals. So we went ahead, got the revolutions, and also recorded the amount of volume, which you can see is very consistent between both designs. We noticed that the 4-wheel and 2-wheel design did not have much difference in the amount of volume, so we went ahead and concluded that the amount of rollers do not depend on the amount of volume that we're outputting. Okay. So therefore, from our experimental data, we entered them in our governing equations. We got our theoretical values and our experimental values, and as you can see, there is some inconsistency with our error due to the fact, since it's being hand cranked, there's a lack of consistency in the velocity, and also because the housing continued to fail for us on our second design as well. Okay, so after our second one, we went ahead and did our final. We made it stronger, more durable, and we did 2 tests. We did a static and a dynamic test. As mentioned before, the static was placed on blocks, and we did it using 3 different types of tubing: a large vinyl tubing, a smaller, and then a silicone. One thing to point out is the dependency of the diameter of the tubing. So for instance, larger diameter for vinyl will produce larger amount of water, volume of water, versus a smaller diameter will produce much less. Another thing that we want to point out is the flow constraints that we have between using no filter and with a filter. The first three values that you see there are the amount of large amount of water being output versus the least amount, as you can see for the last three. Okay, so for the dynamic, we wrote around it and we saw the same relationship, so we can conclude that our values were very consistent, as in the dependency of the diameter of the tubing and also the flow constraints that we have using a filter. Okay. We went ahead also to do water quality tests. We got some sources from various canals. Unfortunately, we're unable to determine the bacteria or any kind of protozoa that could be found within the water. But however, we still had a successful filtering process that you can see with the picture. One thing to point out is the the lab testing that we were unable to acquire, at least to determine all these different bacteria being removed. So this could be an established collaboration that we could have with environmental engineers, that they'd be able to retrofit a filter to our system. Okay. So with the design improvements, we definitely want to have more connectivity points so that it's easier to maneuver. Definitely make it shorter and lighter for the rider. Definitely position the pump somewhere else so there's a steadier flow, and we can remove the process, the recycling process of the system. Also, have a carbon filter or have a stronger filter that will produce lower pressure and higher volume. Okay. These are the standards that we use. We use the ACM for our pipe fittings and the flange bearing inside of our pump. We use the SAE for the square tube in the pump, and the ABMA for the flange bearing and our axle. Okay. Overall, we learned the whole design process, what it takes to build an entire model, also what it is to meet a certain deadline, as well as coming together, distributing all the responsibilities and coming together, having the model going from start to finish. Okay. For our cost analysis, we had an initial goal of $500. As we gathered all the materials, we estimated that our cost would be roughly around $638. But as we put all of our components together, we found that the actual cost was much less, which at $596. So from that, we can conclude that we're a little bit over our initial goal, but we still stayed within the same range. So as of this, we think this will be a successful accomplishment, at least in our part. Okay. Now the collaborations that we want to the non-profit organization we'd like to collaborate with. At least we want to spread the same awareness of water scarcity found in all these underdeveloped countries. Hopefully that they will be able to either pick this up, at least maybe provide the kind of service using this model, or providing this to all families out in these different areas. Okay. As a conclusion, we were able to find this to be a very cost-effective model, because we were able to acquire inexpensive parts, able to retrofit this to any two-wheeled bicycle, also successfully transport, filter water, and once again, we stayed within a range of desired costs. Okay, here's going to be a quick video of our H2Go. So as you can see, the maneuverability of the bike, rather than just going straight, we're able to go around corners. Another thing to point out is that we're able to transport every kind of component very easily. And coming up, you'll see that it's going to be able to retrofit, once again, to any bicycle, just connected to the back of the bicycle seat. And from here, you'll see all the tubing with all the components all fit together, going into our Sawyer filter and into our dirty tank. One thing to point out here is how the mechanism is actually working while we're riding the bicycle. And once again, we wanted to enforce off-road capabilities, so rather than just being on the street, we can go anywhere, gravel or grass. And here's our before and after, with all the components all put together. I'd like to thank you all for taking time to review our project. I hope that this will spread awareness and water scarcity, and hopefully that this project will be able to improve the quality of life. And
Where's the water filter?
It's this
Very
tiny.
small.
Yes.
It's on the side.
Oh, it's that small?
Yes,
Yeah,
yes, it is, which
I'm
is why
looking for
it's
this
such a-
Because of the pressure, right?
Big
Yes.
jump somewhere. Is that a fire line?
No, that's not fire line. That's
No, it's not
probably a
fire
phone.
That's a phone?
Yeah. What's that tall blue?
This is the pre-filter.
That's a pre-filter.
So
Oh.
if you see inside, we have all the meshes,
Oh,
and this is to prolong the filter life.
Before, yeah, this is before the water enters. Like we put it in the dirty water tank, and that's where we put the water in there, and it filters any fresh part.
I have to look at
Sure.
it. I want to look
We
at
probably
the
shouldn't
whole
We
thing.
need a lady to bicycle.
Okay,
go,
so
nothing.
first we put this one here.
One lady should bicycle.
This is the dirty water tank, so you
This
put
is
the
the
water.
dirty
Yeah, so you put this one here, then we fill it with water, and then you just put the tubing and then just start.
Oh, so you do this by hand?
Yes.
Yeah,
Get
yeah.
all the sediment out
Yeah.
of the water.
That's
point
just
of
there.
this- yeah.
That's
The point
just
of
the
this
like
was-
And so this is your first,
Yes, ma'am.
Yeah, that's the first stage.
and then what happens? Then
You siphon through water to prime the system, and then you just run it.
Yeah.
Okay, so you pour this in here,
Yeah.
and this
They
becomes
just
your
siphon,
filtered
yeah.
dirty water, and
Yes.
it goes to
Yes.
the,
Yeah, and then
and
it's
then when it
Clean
goes
water,
to
yes.
clean water, yeah. Pickle water.
Thank you.
Did you do any life test on the pump?
We
You
did
know, run
not.
it and run it and run it and run it, see how long the tubing would last? or,
Yeah.
We did not specifically because we wanted to be able to use any tubing. So it would really depend on the material of tubing. One big thing when we first introduced this project was what the availability of certain tubing would be in a part of the world, any part of the world. So that's why the roller mechanism was ideal, so we could use any size tubing, any material. But no, we did not do life rating.
We ran it all.
Yes, we did run a whole lot.
So, but you didn't keep track of how much you ran it, no degradation on the tubing for the time?
No,
you did
no,
it?
I mean,
I mean, we did test it in different types of tubing, so.
yeah, I mean, it was tested throughout a whole month. We didn't keep track of it, and there was no failure in any part of the
That's the
pump.
same when we started off.
Yeah,
No bearing failure?
nothing,
Nothing,
nothing.
nothing.
The bearing is much more powerful than it needs to be for this specific.
Yeah.
Yes.
I have a question for you. So you did finite element simulation on the bottom of the cart. Why didn't you do it on the housing itself, since that's the thing that was failing the most?
On the housing.
It has another pump, you mean?
Clarify.
Yeah, right.
Pump
Yeah,
house.
so you said the first time through, your housing was breaking, right?
Yes.
And then the second time through, the housing was
Yeah,
breaking,
uh-huh.
right? To me, you put something down on the bottom, right, it can hold water. But the pump itself is very important in terms of the thickness of the walls and
Yes.
everything associated with that. I would be much more interested in the stresses in the housing of the pump than I would be just on a piece of wood on the bottom of the cart.
Yeah, well,
Because that could tell you how thick it should be and all of those things,
oh, I
right?
see what you mean. Why didn't we run stress tests? Basically, it was a trial and error kind of a process because it was very hard to run simulations on it on SolidWorks.
Okay.
For our specific, what we specifically wanted to focus on, it was very difficult to run the stresses of it.
The cake band design that we had at the beginning, I mean, it was a little clip that kept it together. So as you can rotate it,
Yeah.
So why do you think you got failing in the housing?
In this housing, no failure.
No failure in this one?
No, no,
Okay.
no failure.
Okay, all right,
This
so I
is-
thought you said the
This you can
second
grab
was
it and,
failing.
no, that was
Okay,
the
all right.
first
prototype.
prototype. Hold up.
Yeah, the first
Yeah, the first
prototype.
prototype.
Yeah.
So the first one you got failure because.
Yeah, it was
stress
so
was-
thin, yeah.
The material was just.
Yeah,
I could
so-
bend it with my
Right,
hand.
yeah, exactly. One other quick question, can you go to the cost really quick?
Sure.
So the cart cost you $200, right? The whole cart. Is that, so you bought, is that with what, buying the recycle, what is in the $200 for the cart?
That's our conduit pipe, our fittings, plywood. The axle actually got it from a two-wheel picker, it's like $10 or something like that. So that saved us a lot of money. They recycled the gears, so that was.
I would just say, $600 still seems like a lot if you're gonna bring it to Africa and hope to, so, what is in the 200, so all of the, what's the big part of the $200? What's the most expensive?
The pipe fittings.
The pipe fittings.
The reason for the pipe fittings is so that you could take it apart and put it back together, basically. So
So that we can
in
ship it
terms
apart.
of shipping,
Mhm.
that's the basic.
Yeah, maybe, I don't know, PVC, you could just
Yeah.
cement PVC together, you think it would, I don't know, I'm just
It-
trying to throw stuff
Worried
out.
about the
Yeah.
durability of it.
Yeah.
Yeah, we just wanted to be durable.
Yeah, if you make it for $100, if you make this whole thing for $100, though,
Yeah.
you make 6 of them.
To be honest, it would be cheaper if you were mass producing it.
Yeah.
It would, ultimately,
Right,
it
right,
would be
right.
cheaper if you were getting all the materials in bulk.
Oh, sure,
Yes.
but, anyway, okay, yeah, that's fine. Oh.
If you did tube bending rather than pipe, you would find it much cheaper.
Correct.
Right,
Yeah,
exactly.
exactly.
We were just worried about making it congruent with the tube bender we had, and we're handheld, so we didn't want it to be all lopsided, so safe and sorry.
Yeah, but the automatic ones would be, everyone would be
Right.
the same.
Right.
Go ahead, you go.
Actually, I noticed in your analysis, you had the tanks in line, but here you have it next to each other, and I'm looking at this design, you're gonna have to wait in the back of the cart, so it's gonna wanna push the whole arm up. You know, have you thought about analyzing like this instead of the way you showed it in the presentation?
The way we had it initially, you're correct, it was front, but once we got this axle fitting, we knew that we needed to put the pipe in the front so that it would be able to retrofit to any pipe easily and be kind of its own self-incumbent machine. We didn't do any analysis on the backside of it wise. Like I said, we did stand on the skeleton as a whole, my own weight on there, and if I can stand on it, it's fine. Figured 5 gallons of water is no problem,
Yeah.
and even, greater tanks too.
Okay. Again, I'm going to ask each and every one of you separate questions. To start with the peristaltic pump, why was the decision to use a peristaltic pump in the first place?
It is easy to retrofit to a mechanical device powering it. It can run up to, initially we didn't have a pre-filter in our design, so it can push up to 60% of solid material. It's easy to clean, easy to maintain, it's easy to fix in case of failure.
Okay, in your experimental results, you talk about a 4-wheel system
Yeah.
and a 2-wheel system.
Yes.
But you created a 1-wheel system.
Yes.
Why?
There was no advantages to the 4-wheel or the 2-wheel.
So where's the data on the 1-wheel system?
We don't have it.
We did do a 2-wheel and a 4-wheel and saw the flow rate wasn't
Yeah.
very much different.
I know, but you ended up with a 1-wheel.
Right.
If you ended up with a 2-wheel, I would have understood
Yeah.
that. Okay, so I'll go to the second one here. Why did you see in static a difference at the same diameter for the vinyl material tubing and the silicone tubing?
Can you repeat the question?
Okay, you used in your experimental work vinyl tubing and you used silicone tubing,
right.
and you had the same diameter tubing, ID,
Mhm.
yet you had substantial differences in
Okay, yeah,
flow
that's
rates.
because of the material. It's because the vinyl is a lot more durable, and so when the occlusion is happening, that vinyl material just makes it that it flows a lot better. The silicone is not as a strong material, and that is why the flow rate was also very, it was lower as well.
Okay.
It was all the material that we chose. That's
Now
what-
again,
that's-
durability-wise,
Durability, yes, and the vinyl actually, it's the one that will last a lot longer.
would last longer?
Yeah, it will last a lot longer because it's, it's stronger as well. And we just use the silicone one because on the first prototype that we made for the pump, we just couldn't get it to work with the vinyl, but that's why we chose the silicone. But now, once we got this one working, the vinyl worked a lot better, and that's what we needed. We needed a better housing for our pump.
Okay, very good. And again, I kind of asked the same kind of question he asked. When I look at the design, I would have thought you'd been symmetrical around your wheels, load-wise. Not structural. I understand the structural members would have been capable of handling the load. But when I put the water in the bag, what does it do to your tongue weight?
It's gonna,
Okay? And now, whereas this should probably, and if it's not connected to the bike, and you put water in there, where's the cart going to end up?
right.
So anyway, that's just a feedback statement. see what else I had comments on your report. I just wanted to, in your report, you say things, it's clear to me that you had written the front half of the report for last semester, and you didn't go back and reread it. And I'll use an example. You said here, sections of the proposed design need to be revised once the design is selected. Due to the described positive and negative features, we are still undecided on the exact model. And that's in your finished report. Okay, so strong suggestion, read what you do. You also had figures with no mesh, with no units. AutoCAD files, drawings with no units, and I like units on drawings. Okay, so that's the feedback. Let me ask you a question on the filtration.
Okay.
The comment was made that this filter is good for 1 million cycles, a 1 million cycle life. Do you really think in this application you're going to get 1 million cycles out of that?
Not realistically. I mean, we don't, we wouldn't really know, but in comparison from, at least for our use, we're not using such high pressure. We're just using at least the peristaltic pumper. Our pressure at least was around 11 psi. So we don't think that at least that filter, in a way that I guess you're stating, the billion gallons, there's not really going to be much failure to it.
I mean, my worry is that this can handle 60% metal
Correct.
Loading of particles. That filtration system isn't necessarily going to keep all the particles out. But if you hold it up, I can see all the way through.
Yeah.
So I'm going to be loading up this little filter,
Right.
and it's not self-cleaning.
No, actually, well, this is not self-cleaning. You're correct. Only things you can replace the cartridge, but with the pre-filter, initially what we're trying to do is exactly we're trying to just remove any kind of heavy materials or any kind of we'll need it from large.
I mean, would this
systems.
take sand?
Yes, this will take, because there is on the bottom of the last one, it's a cloth, so it's very the mesh is like almost, I wouldn't say to a micron, but it will catch anything, for instance, sand, and you'll be able to remove it in case you need to be cleaning it. You can just remove it, clean it out, and then just put it right back together.
Okay.
Right.
Very last statement you made in your report. You said this would be self-cleaning.
Which one?
The system would be self-cleaning. And I have that in here, and that's not self-cleaning. That's my last question.
Okay. I don't know what we specifically stated with the self-cleaning. I think we probably meant that for the pre-filter. Could you state?
Yeah, in your report it states that filters, and these are directly your words,
Okay.
filters that can be self-cleaned and long-lasting will be incorporated.
Well, like I said, our focus was mostly on the mechanism of it. So that's where we wanted at least collaborate with the environmental engineers, because once again, we're not environmental engineers. That's something that they could probably, like I said, collaborate with us to make some kind of filter that's, once again, either be self-cleaning and be more durable with, for instance, a 1 million gallons life cycle.
Thank you.
Okay. Any questions?
Can I throw a couple more?
Sure.
Can you go back to your simulation?
That's all right.
Just, I'll do them quick.
Okay.
This is more suggestions.
Okay.
Okay.
Sure.
I'll keep going back, keep going back.
We're almost there. Bear with us.
It's like the music stands.
Yes.
Almost there. One more, right?
Keep
Keep
going.
going.
Keep going.
There you go.
Do you want to go from the beginning?
Yeah, no, that exact one, next
That
one.
exact one? Okay.
Yeah, so I'm sitting 30 feet away and I can see your elements. I don't know if that's, so those, obviously each one of those things is an element, I'm assuming, right? In your simulation?
You're talking in terms of the mesh?
The mesh, sure, yeah.
Yeah, we had trouble meshing it. We took it apart, put it together, and it for some reason wasn't working. So this was the best design we could come up with. Well, that we could still have the most components possible.
Well, just in general, so separate from the simulation itself, right? This is not going to give you any realistic information at all if your element size is that big. We're talking about maybe 40 elements in total on that whole entire plate, which is the size of a table, right? You need thousands and thousands of elements, right? We shouldn't be able to see any of that. You can see the difference, right? Each individual triangle there is an average of that entire area, right? So there could be really, really high stresses at small points right there, especially if you have stress concentration, that are completely removed, right? Because they're averaged over that entire element. So you have to be very careful when you're looking for things like max stress on your element size, right? Because those are averages. Those are all averages and not point values, right? So be very, very careful with that. One more quick.
The question that the number of elements you have are 6,000, right? Meaning
6,000,
and
yeah.
maximum 3,000, right? So the triangle is just the post-production of the color.
No,
It's not
it's
the size
not.
of the elements.
It's not though. It can't be.
Look at the numbers. that
But
you
think
have.
about distribution of stress,
Right.
right?
Exactly.
So that triangle, no way on earth, in my opinion, is putting a cylindrical thing on a plate going to give stress concentrations that look like a triangle.
On SolidWorks, it's
Right.
just the way they show you the information. It's not the mesh itself, not elements itself. Because you don't have.
Go to the previous one, right? Why don't we see huge triangles here?
Right, I mean, you can. But that's
Because you see number of nodes is 16,000 in that case, right?
exactly.
Yeah, so the other one was
That's the number of
3,000.
nodes, that's the number of elements, so different
Sure,
things
so
you
nodes and
show
elements are
exactly,
connected
but
though,
you
right?
show
And you
two
gotta
elements.
connect nodes on elements, right?
That's what I'm saying.
So just switch between the two really quick and you see a huge difference in what they look like,
Yeah,
right?
sure.
3,000 versus 16,000. That's what I'm saying, yeah.
Anything else? Anyone? Thank you so much.
I got one more quick question. Now, the filter that you used, did you analyze
that's
other
the exact
different
number. That's not
filters
the number.
before you picked this particular model?
Yes, we did. We actually analyzed the McMaster car. We couldn't find a filter that didn't need enough, how would I word this? The pressure. It was the pressure was really our sticking point on the filter. Also, the cost and life rating. So this was the best option we could choose for this specific